The rotating loop is the prototype of one type of alternating current generator or alternator. It develops the sinusoidal varying EMF. The EMF is maximum in absolute value when theta equals 90 or 270, and the long sides are moving at right angles to the field. So we can see that when we're in this position here, I'm saying that it's right angles to the field now, field's going up. So in fact, when this is exactly, you can see the rotational part there is at 90 degrees to the field, so we've got maximum EMF when it's in this orientation. The EMF is 0 when theta equals 0 or 180. Looking at it in end view, when we're down here, the B and the velocity vector now are collinear, so that there's no force at that point, so you get 0 EMF at that point. In other words, the sides are moving parallel or anti-parallel to the field. The rotating loop in A can serve as the source of an external circuit by the use of slip rings. So we've got these two slip rings drawn on here. So you can see we've got the loop round here. One of them is connected to this slip ring and the other loop is connected to this one. These two slip rings don't touch one another. So what you can do now is put brushes on here, and you can see as it turns round they're both independent on these rings. These rings are not in contact with each other, but they are contact to these brushes here. So as it spins round, you can see that you're going to generate this sinusoidal voltage on these output terminals here. This graph of VAB is a function of time. Now what I've done here to make this really easy to follow what's going on, I've placed down an end view of the actual loop, and then I've described what's happening with the EMF on each of these positions. Number one, it's when the angle here is 0. So you can see that the angle here at number 1 is 0, so we're flat down here. And the force is 0 as velocity is parallel with magnetic field. I've just written force here, but I could have written EMF. Number 2, the angle now has increased a little bit, so I've drawn number 2 as here, so you can see like it's going up now in this direction. Force at this point is into the page, so if we cross V with B, in other words, if we go like that, you can see it's going into the page, yeah? So the force is into the page at this point. Number 3, the force into the page maximum. So when we're at number 3, as I said, because that's 90 degrees now, the velocity now of this moving part of the coil now is at 90 degrees to the magnetic field. So at number 3 we're into maximum, still going into the page, and number 3 is shown here. You can see that it's at the maximum. And then number 4 is still into the page. So at number 4 now we're still into the page. You can see that if you're turning the V into the B, you're still into the page. EMF is not as strong there now, it's sort of beginning to come down. And then when we've rotated right round to here again, then of course the velocity vector is now exactly opposite to the magnetic field vector, but it's in the same, it's in parallel, completely in parallel with it. So there's no EMF at this point. So at 5, the force 0, EMF 0, as the velocity is anti-parallel with the magnetic field. And then here at 6, now we've got a different, we can see that the velocity vector now is going down. So if we screw the velocity vector into the B, we're going up. So now it's coming out of the page. So the EMF now has changed direction. So at this point here, number 6, we can see there's a change of direction. It's coming out of the page. So if you look at 6, yeah, look, now it's changed direction. We're down at this side, the axis here. So on number 7, you can see number 7 here, we're down here. Now at number 7 again, we're at maximum EMF here, because look, the velocity is at right angles to the magnetic field. So at number 7, force out of the page is at a maximum. So the EMF is in this direction now, it's at a maximum, yeah? So that's at 7. Then at 8, force out of the page again, it's come down a little bit. So you can see if you just follow that through, it's gonna map out this sinusoidal curve here, yeah? And that's a really easy way to see the correlation between these and that. A similar scheme may be used to obtain an EMF that, through varying with time, always has the same sign. We connect the loop to a split ring this time, or commutator, as in this diagram B. At angular positions where the EMF reverses near theta equals 0 or 180, then you can see here that there's a split ring here. Now it's going to swap over. Those leads are going to swap over, and it's going to continue to be positive because they'll swap over. Whereas before it was going through because their rings are continuous. Now they swap over, so that you can see how that occurs. So you can generate a DC voltage now with this. Same thing again. You can now follow these through. Yeah, we're going to get the same situation, but in this time they're not going to come out of the page. They're always going to be going into the page. Yeah. So when you get to 5, everything's going to be the same up to 5. But then when you get to 6, instead of it going out, it's still going to be going in. Yeah. So I hope you can see that. These 3 diagrams really make it easy to understand how an alternator generator works, really, if you just follow those through. This device is the prototype of a DC generator. Commercial DC generators have a large number of coils and commutator segments. Their terminal voltage is not only unidirectional but also practically constant. That's a really good example of how the induced EMF can be used in a real practical sense. You can make AC and DC generators now and understand how they work.